code rarely works the first time. In this section, we learn debugging, the art of finding out why your code misbehaves and putting it right. A bug is simply a mistake that stops your code reaching its goal. Debugging is finding and removing those bugs, and it's one of the most fundamental skills in programming. Here's what you'll be able to do by the end. Say what a bug is and what debugging is. Tell a compilation error apart from a runtime error, and recognize the common Python errors: name error, type error, attribute error, and syntax error. And use 3 friendly techniques: print debugging, scope debugging, and rubber duck debugging. Let's begin. Remember the programming flow: write, run, evaluate. Debugging is what you do when that evaluation shows a problem. Maybe the code threw an error. Maybe it ran fine but gave the wrong answer. Either way, there's a bug to chase. Here's the key mindset: don't just stare at the code hoping the answer jumps out. Debugging is research. Gather information until the problem becomes clear. Errors come in 2 broad flavors. Compilation errors are problems inside the code itself. You could spot them just by reading it. Runtime errors only appear when the code actually runs, often because of the particular data it meets. A program to delete files in a folder might be perfectly written, yet still fail on an empty folder. That's a runtime problem, not a flaw in the code. Let's tour the common Python errors. A name error means you used a name that doesn't exist, like saying give her the book without ever saying who her is. A type error or an attribute error means you asked for something that makes no sense, the length of a number, or whether the number 5 ends in the letter D. And a syntax error means Python couldn't even read your line, like writing print 5 with no brackets. Each message points you at the line and the problem. The first and simplest technique is print debugging, sometimes called tracing. You scatter print statements through your code to watch how it flows. Imagine a short program that never seems to finish. It just runs and runs with no output, no error. Add a print after each line, and you can see exactly where it gets stuck, or which line is running over and over. The flow becomes visible. Here's a count up then down program that hangs. We add print statements through it and run again. The trace shows the first loop finishes, the second loop starts, and then it just repeats, never finishing. Now we know the bug is in the second loop. Looking closer, we're adding 1 when we should be subtracting. One small fix and it counts down properly. Sometimes knowing where isn't enough, you need to know what the data is doing. That's scope debugging. Instead of printing just to trace the flow, you print the value of a variable at each stage, to check it's what you expect. Picture a program averaging 12 grades. It touches all 12, yet the average is wrong. So we print the running total step by step. By hand, the average should be 89, but the code says 6.8. So we print the running sum after each grade. After 1 grade, it's 100, correct. After 2, it should be 195, but it shows 95. After 3, it shows 93, not 288. There's the bug. The sum isn't growing, each grade replaces it instead of adding to it. We fix that one line, and the average comes out right. The third technique sounds odd but works beautifully: rubber duck debugging. The idea: keep a rubber duck on your desk and explain your code to it, line by line out loud. So often, the simple act of describing the problem from scratch reveals the answer. It needn't be a duck, a cat, a colleague, anyone. Explaining is the magic. Let's recap. A bug is a mistake that stops your code reaching its goal. Debugging is finding and removing it. Errors split into compilation errors, found by reading the code, and runtime errors, found only by running it. Watch for name error, type error, attribute error, and syntax error. And keep 3 tools handy: print debugging to trace the flow, scope debugging to check the data, and rubber duck debugging to explain your way to the answer. This lesson is based on Section 1. 3 of Introduction to Computing by David Joyner, used with permission. The concepts are taught in original words, and every diagram was recreated as an original animation. That completes Unit 1, well done, and on to real Python.